Please let me introduce our work, Logic Gone Astray, a security analysis framework for the control plane protocols for 5G basebands. 5G is a global standard for cellular networks, and 5G devices are now widely used in autonomous vehicles, cyber physical systems, and some other mission-critical services. The security and privacy of these cellular devices are important. It is imperative these 5G-capable devices correctly implement the protocol specification to meet the security requirements. Otherwise, violates the security policies like authenticity, confidentiality, may lead to many critical issues such as the user's information may got leaked and his service may got downgraded or disrupted. So here comes up our research question. Is it possible to develop an automated framework to efficiently identify security policy violations in 5G UE implementations? However, the first problem we encountered is that there is no such a list which contains a complete set of security policies which we could directly apply for testing. In this case, to achieve our goal, we designed our framework 5G base tracker, which the key intuition is differential testing. Since those 5G devices are implementing the same protocol, if two devices behave differently for the same input, then at least one device is implemented in a wrong way, or this is the case that underspecified in the specification. Building on this intuition, we will generate message sequence, send them to the devices, and see whether they are responding in a different way. Once the deviation is got, we leverage this deviation as a guidance, then search the specification to see which output is wrong and what security property it violates. Based on this pipeline, the first question naturally arises here: how to generate the input? Generating random inputs will not work because 5G control plane protocol is stateful, and also we are doing the over-the-air testing. This is a bit slow, and if we generate random inputs, it will take a lot of time. So we need a smarter way to generate the input sequence instead of randomly generating them. So we designed the state-sync module to synthesize finite state machine to model each device's behavior. And then to identify the differences between the finite state machines, we designed another component. We call it devscan. After obtaining all the deviations, we designed another component. We call it devlizer. This component is mainly responsible for triaging the deviations. Let's take a look at the state sync first. One technique we used here is active automata learning. Let's see how it works. Actually, active learner works iteratively in the following two stages: hypothesis construction stage and model validation stage. In hypothesis construction stage, the learner sends a series of membership queries to the system, and based on the response, build the hypothesis finite state machine model. In the hypothesis validation stage, the model validator sends equivalence checking queries to check whether the hypothesis is equivalent to the system under learning. If they are equivalent, the learning is complete. Otherwise, the model validator will say the hypothesis model is not correct and return a counterexample back to the active learner. Based on that counterexample, the learner will generate more membership queries to learn and refine the hypothesis model. There are some previous works which directly apply active automata learning technique to infer the finite state machine from the device. However, they suffer from the problems of learning efficiency. The first challenge is that the active learner at first do not have any idea about the protocol interactions. It will generate many meaningless queries at the beginning to explore. The second challenge is that active automata learning also require an equivalence oracle to validate the hypothesis model. However, this results in a very large number of equivalence checking queries being generated in the model validation stage. More importantly, most of them are not real counterexample which could help update the hypothesis model. More than those, since applying active automata learning on device, it requires over-the-air queries, which is pretty slow. If we had such a huge number of queries to extract the finite state machine from the device, it could take over 1 month. To address the first challenge, we introduced passive automata learning to help accelerating. We first collect some normal 5G network traces, then feed them to a passive learner to synthesize an initial finite state machine. This process is fast, since passive learning does not require any over-the-air queries. This initial finite state machine will guide the active learner when start. In this way, the active learner can get some knowledge at the beginning instead of generating a lot of over-the-air queries to randomly learn the finite state machine. So the learning efficiency can be improved. To address the second challenge, we leverage another insight. Since all the devices implement the same protocol, the finite state machines would largely be similar, and any counterexamples found during the finite state machine construction of one device is highly likely to be the counterexamples for other devices as well. So we can reuse the counterexamples found previously to accelerate the learning. So once a counterexample was found for one device, the active learner will store this counterexample. When it starts constructing the finite state machine for the subsequent phones, it will first try out the counterexamples stored to see whether they can be used to update the finite state machine model before using the model validator to search. Here's the workflow of StateSynth. The input for this module is a set of 5G UE implementations. The output will be a set of corresponding finite state machines. We first leveraging passive learner to synthesize an initial finite state machine to help active learner in the beginning phase. Then, during the active learning phase, the active learner will query the UE implementations and got responses from them. Before using model validator to search the counterexample, it will first try out all the candidate counterexamples saved previously, as we discussed. Then we construct the finite state machines for all the devices sequentially until we construct finite state machines for all the deviations, for all the devices. After constructing finite state machine for each device, we start identifying deviations between them. So we designed DevScan module that can take the finite state machines as input and output the deviations. We built the DevScan based on a previous work. However, the previous work have a limitation that prematurely stopped their exploration for different variations of a deviation. This implies that if an attack can happen in different sequences, the previous work will miss them. For example, I have two simple finite state machines here, which contains a deviation I marked as red. The previous work can detect one path, which could lead to this deviation. However, there's another path could also lead to this deviation, but it was actually cannot detect it by the previous work. To overcome this limitation, we incorporate a graph traversal mechanism. Specifically, when a deviation-inducing input sequence is found, we will perform a graph traversal from the initial state to the state where the deviation is found and report all the paths that can lead to this deviation. So our tool DevScan takes all extracted finite state machines as input, reduce the problem to a model tracking problem, and check the property that, given the same input message sequence, whether two finite state machines are giving different output. When a deviation is got, all the unique paths that could lead to this deviation will also be logged. After obtaining those unique deviations from DevScan, we also need some other techniques to help automatically triaging the deviations. For example, identify whether a deviation violates any security property or not. So we designed the third component, devlizer. Initially, all the deviating traces in the set, we mark them as unresolved. The devlizer then first picks an unresolved deviating trace, and the security expert will consult the 5G specification to identify the correct behavior for the input sequence and write one or more LTL properties, then return them back to the devlizer. Based on the LTL property, devlizer can automatically triage a set of unresolved deviating traces using model checking. And the security expert will work with devlizer iteratively, which means when devlizer encounters the deviating trace which cannot be resolved by the current property set, the security expert will keep adding LTL properties into it until all the deviating traces got triaged. For evaluation, we tested 17 commercial 5G devices from the following baseband vendors, and also 2 open source UE implementations. The devices we tested including Android phones and iPhone. To evaluate StateSynth, we compared to a previous work which applied active automata learning directly. As shown in the figure, the red curve, we call it DIQE star. It requires around 73,000 queries to extract all the finite state machines. whereas our state synth only requires around 26,000 queries to extract all the finite state machines. This demonstrates that the state synth brings significant improvement in finite state machine learning efficiency. From the findings point of view, we uncovered 22 unique issues. Among them, 13 could lead to exploitable attacks. We reported our findings to the corresponding vendors and GSMA. In total, we got 12 CVEs from the vendors and 1 CVD from the GSMA. So there are some interesting bugs. I will just talk about the most impactful one we found for the time's sake. We found a serious bug in Exynos basebands, namely 5G aka bypass, which affects a majority of mainstream Samsung and Google Pixel phones in the real world. Please let me briefly introduce how this vulnerability can be exploited by the attacker. This attack begins when the victim device initiates a connection to the fake base station by sending a registration request. Then the attacker will respond to the UE with a plain text registration accept message directly. Importantly, this message has a manipulated security header, as shown in the figure. And here it is actually a semantically incorrect message. However, surprisingly, the Exynos baseband accepts this message directly and respond with a registration complete, which means the attacker successfully bypassed the authentication and key agreement procedure directly. Once the UE accepts this registration accept message, it proceeds to believe it has already established the trusted connection and completes the registration process. The victim device then sends a PDU session establishment request, anticipating the start of a secured data session. The attacker then further exploits this opportunity, crafting a PDU session establishment accept message and encapsulating it into a downlink NAS transport message. The attacker then crafts a plain text RC reconfiguration message that carries the above message segments and sends it to the victim. The RC reconfiguration message here is also a malicious message, which contains a prohibited information element for establishing the bearer. After the above steps, the attacker can provide the victim with unprotected 5G data sessions, which severely breaks the user's privacy. Let me show you the exploitation demo. Here is our attack setup. We have a USRP B210 serving as a fake base station and a Samsung Galaxy S21 as a victim phone. As you can see from the Wireshark terminal, after sending the attack message, registration accept with security header 4, the phone returns registration complete directly and the PDU session establishment request, which means the authentication and security mode control procedure have been bypassed. After that, the phone have already got the internet access. It starts sending some plain text DNS packets, which means the attacker can profile the user activity, such as which website the victim is browsing. Also, from the user's perspective, the victim user can browse the websites and also watch the YouTube video without any warning from the phone. So the victim may not aware of he has already connected to a fake base station. But the victim's traffic is monitored by the attacker now. Okay, to summarize, we designed 5G base tracker and automated security analysis framework for 5G basebands. We designed a new approach, hybrid and collaborative learning, which significantly improved the efficiency for constructing the finite state machines. We also designed a deviation analyzer, which semi-automated the process of triaging the deviations and root cause analysis. Also, we have open sourced our work at GitHub. That's all of my presentation. Thanks a lot for attending. I'm happy to take any questions. Thank you.